Standing waves have nodes that do not vary in position over time. Think about a jump rope. With two people on the ends, it forces the ends to be exactly at a certain height, and everything else in between can vary. Now, standing waves are typically defined by their boundary conditions. For instance, let's imagine a pressure or sound wave being created in an open-ended tube. Well, outside the tube, we know the pressure must be equal to the atmospheric pressure. So, right at the edge of the tube, the pressure has to be set to be these values. So, what other possible waves we can get if we have these nodes at the ends of the tube? Well, in red we can see a wavelength that is twice the length of the tube. In blue we could see a wavelength that is equal to the length of the tube. And in purple we can see the wavelength that is 2/3 the length of the tube. Now, how am I figuring this out? Well, I can just see that this is about half of a wavelength that will have two nodes there. And I just increase the number of nodes for each increasing system. Now, the allowed wavelengths here, and these are the numbers I described, depend purely on the length of the tube and whatever number harmonic we're looking at. So here you can show that 1, 2, and 3 actually are just plugging in m's here. Now, this isn't super useful because we often think of sound as frequencies, so we can represent this using frequencies by relating f, v, and lambda. So here, if you want the mth harmonic, you plug in an integer value of m, and that'll tell you the frequency allowed in an open-ended tube. Now, the same idea can happen when we have a closed-end tube. Here, we have a node on the open edge because it has to be at atmospheric pressure, but at the closed end, it has to be at maximum pressure. So there are certain allowable wavelengths that have this node at one end and antinode at the other, and this is described by length equals m lambda over 4. Now, again, let's represent this in terms of frequency, and we can see that the frequencies available to a closed-end tube are mv over 4L. Now here, what's really important is that m has to be odd. We're only allowed the odd frequencies in a closed-end system. So, let's give you some terminology. The mth harmonic just corresponds to whatever number I plug in. So if I plug in a 1 here, that's the first harmonic. If I plug in a 3, that's the third harmonic. Now, I can also call things overtones. And the way overtones work is that they start counting at the first harmonic above the fundamental harmonic. So here, the fundamental harmonic is lambda 1, or described by lambda 1. So the first overtone would be the next one, which is here, the second harmonic.